This project is based off of the Systems Engineering V model and describes the design, implementation, and testing of a frozen shoulder expert rehabilitation system. Team members that worked on this project are Farzad, Blaine, Faisal, Will, and Emmanuel. Frozen shoulder is a condition that is characterized by pain and stiffness in the shoulder joint due to scar tissue buildup, leading to a temporary loss of range of motion in the upper arm and pain that worsens at night. Patients are typically in the 40 to 70 age range, and women are affected more than men with a 3-to-1 ratio. Frozen shoulder occurs in 3 distinct stages. In stage 1, known as the freezing stage, patients experience severe pain with a gradual loss of their range of motion. In the second stage, or the frozen stage, they experience pain at the extremes of their range of motion, and their range of motion becomes very limited. In the third stage, or the thawing stage, they experience a gradual return of their range of motion. Physical therapy is an essential part of treating frozen shoulder and is highly recommended in stage 1. In the latter stages of the condition, when range of motion is very limited, surgical treatments are recommended more. However, the patient still requires physical therapy after surgery. Shoulder range of motion is measured in 4 different movements: flexion, adduction, extension, and abduction. Practitioners use a goniometer to measure the angle between the arm's resting position and the highest point the patient can move their arm to for each movement. Patient progress is calculated manually by comparing the current and previous range of motion measurements. During the treatment process, frozen shoulder patients themselves are the primary stakeholders. In rare instances, when they need surgery, they visit an orthopedic surgeon. However, as mentioned earlier, a big part of treatment is physical therapy, for which the patients must visit a physical therapist. At the beginning of their physical therapy session, the physical therapist or their assistant typically uses a goniometer to measure the patient's range of motion and calculates their progress manually. They also provide exercises that the patient must perform while they're at the clinic. At the end of the session, the physical therapist provides a list of physical therapy exercises that the patient must perform between sessions. To determine the frequency of these at-home exercises, a survey of patients that had physical therapy for a shoulder condition was conducted. 68% of the respondents indicated that they had to perform at-home exercises during the course of their treatment, with 80% indicating that the frequency of their at-home exercises was 3 or more times a week. However, only 20% answered that they performed all of the prescribed exercises. Insurance companies are also another stakeholder in the system. They are primarily motivated by profits, which means they often want the patient to start with the most inexpensive treatment option possible, which might not necessarily be the most effective one. Furthermore, they provide limited coverage and only cover the first 60 sessions, and even the patient is still responsible for their copay. From our stakeholder analysis, we identified 2 performance gaps. The first being that there is no service available that monitors whether or not patients are complying with at-home therapy exercises. The second performance gap is that insurance companies only provide limited coverage, placing a huge financial burden on the patient's shoulders when their coverage ends. From the performance gaps, the problem statement was derived, which is that there is a lack of remote monitoring to ensure correct exercise performance, leading to a need for a system that provides remote monitoring to ensure patients perform exercises correctly and can autonomously measure range of motion progress. The proposed concept of operations consists of a system that objectively measures the user's range of motion and monitors exercise performance. An accompanying mobile health application provides a platform for healthcare providers to remotely monitor patient progress and enables them to provide physical therapy exercise recommendations or modify current exercises based on progress results. To fulfill the proposed concept of operations, 3 sets of requirements were derived. Range of motion requirements ensure correct exercise and movement performance in 3D space. Interface and design requirements ensure that the system provides remote monitoring, range of motion progress tracking, and that the physical weight of the device is less than 1 pound. Usability requirements ensure satisfactory user experience with the mobile application and the wearable device. In order to fulfill the proposed concept of operations and track arm movement in 3D space, 3 design alternatives were identified. First, a custom wearable device that uses an inertial measurement unit and a muscle sensor to track arm movement. Second, a smartwatch such as an Apple Watch. And finally, a motion tracking device such as a Microsoft Kinect. The 4 attributes that were evaluated were range of motion measurement accuracy, muscle sensor accuracy, physical weight of the device, and an option for remote monitoring. A multi-attribute pairwise comparison was conducted to determine the weight of each requirement. The results indicated that the wearable device provides the most utility. Sensitivity analysis of the design alternatives indicate that the wearable device provides the most utility for all weights of remote monitoring capability and range of motion accuracy. However, the motion tracking device is the preferred alternative when the weight of the muscle sensor accuracy and physical weight are below 18% and above 32%, respectively. The prototype consists of 2 modules, a wearable sensor device that the patient wears on their upper arm, and a mobile health application. The wearable device uses an inertial measurement unit and a muscle sensor to track arm movement, while an Arduino board processes data from the 2 sensors and transmits them to the computer. The inertial measurement unit consists of 3 sensors, an accelerometer, a gyroscope, and a magnetometer. Range of motion in 3D space is determined by calculating Euler angles, which are pitch, yaw, and roll from the XYZ values of the three sensors. In addition, a centrifusion algorithm, namely the complementary filter, was implemented to compensate for long-term gyroscope drift and short-term inaccuracy of the accelerometer. The app home screen provides the option of logging in as a patient or a provider. First, we will look at the provider. The provider, or the physical therapist, logs in using their username and password, and then will see a list of their patients. The provider can either view one of their current patients or add a new one. Looking into the patient portal, the provider can access the patient's progress as well as their exercise plan. The provider can then modify the exercise plan based on the progress of the patient. Finally, the provider can also look at the patient's calendar as well as contact him directly within the app. The patient logs in using an access code given to them by their physical therapist. On the home screen, they are provided the option to check their range of motion for the 4 movements. The app provides written as well as video instructions on how to perform flexion, extension, abduction, and adduction. As they perform each movement, the inertial measurement unit and the muscle sensor monitor the movement of the user and autonomously record their range of motion data for each movement. If a user performs a movement incorrectly, the app alerts the user to redo the movement. When all 4 movements are completed, they are presented with their current range of motion. The patient can also check their range of motion progress on the progress screen. The patient can also use the app to perform their prescribed exercises by clicking on the Exercises button. When they open it, they are given a list of each exercise they are prescribed. By clicking on an exercise, written and video instructions will pop up on how to do the exercises, as well as their given number of sets and repetitions. The system is monitoring their movement during these exercises to ensure that they are performing them correctly. Lastly, the patient can view their calendar to see their upcoming exercise plans. The full demo video can be viewed by clicking on the link in the box below. Verification included testing the accuracy of the inertial measurement unit by comparing the accepted value found by motion tracking software to the angle outputted by the inertial measurement unit. Test results showed that for all 4 movements, the prototype was initially inaccurate, but at the max ranges of motion, the prototype was correct. This is due to the motion tracking software always initially reading 0, but the inertial measurement unit picking up the slightest movement in the upper arm, creating a difference. Statistical analysis of the results proved that there is no statistical significant difference between the prototype and the accepted value. To test the usability